Okay, hello everyone. Let us continue the second part of today's class. Okay, so we have talked about the Wang et al. And the title of their paper is Dense Femto Cell Networks Power Self-Optimization, an Exact Potential Game Approach, which is published in International Journal of Communication Systems in 2016. Okay, so in Scutari et al. 2006, okay, is this the first related work? The authors modeled and analyzed the problem of power control using potential game theory. Okay, what is the potential game theory? Okay, please look at the handout. Okay, page 83, problem 1. What is the potential game theory? Solution. In game theory, a game is said to be a potential game if the incentive of all players to change their strategy can be expressed using a single global function called the potential function. Okay. Okay, let us go to the next page. Potential games have been used in the following two related works. The first is Wang et al. In 2016. Okay, is this related work? And the second is Zhao et al. In 2014. Okay, is this related work? As well to analyze effective channel allocation strategies for the downlink operation of multi-cell networks. In LH et al. 2012, okay, in the previous page, it is the second related work. The problem of channel allocation in OFDMA systems has been investigated using a two-sided stable matching game formulation. In Zhang et al. 2014, okay, Zhang et al. 2014, the authors investigated channel utilization via a distributed matching approach. Okay, next we will talking about the spectrum access as matching and graph coloring problems. Another set of related works is concerned with modeling spectrum access problem as a matching problem between channels and users. In Naparstek and Leshem 2014, okay, this one, Naparstek and Leshem, and the title of their paper is Fully Distributed Optimal Channel Assignment for Open Spectrum Access, which is published in IEEE Transactions on Signal Processing in 2014. Okay, the authors developed a fully distributed auction algorithm for optimal channel assignment in terms of maximizing the user sum rate. Okay, do you know what is the meaning of auction? Okay, its Chinese meaning is 拍卖. Okay, the expected time complexity was analyzed in Naprostek and Leshem in 2016. Okay, here, Naprostek and Leshem, and the title of their paper is Expected Time Complexity of the Auction Algorithm and the Push Relabel Algorithm for Maximum Bipartite Matching on Random Graphs, Random Structures and Algorithms in 2016. Okay. Okay, a low complexity distributed algorithm has been developed in Leshem et al. In 2012. Okay, Leshem et al. In 2012. And the title of their paper is Multi-Channel Opportunistic Carrier Sensing for Stable Channel Access Control in Cognitive Radio Systems. IEEE Journal on Selected Areas in Communications in 2012. That attains a stable matching solution where the achievable data rates were assumed known. Okay, in the following four related works, let us see. The first one is the Bistritz and Leshem in 2018A. Okay, let us see. Bistritz and Leshem, the title of their paper is Approximate Best Response Dynamics in Random Interference Games, which is published in IEEE Transactions on Automatic Control in 2018A. And the second related work is Bistritz and Leshem in 2018B. Okay. Bistritz and Leshem, the title of their paper is Game Theoretic Dynamic Channel Allocation for Frequency Selective Interference Channels, which is published in IEEE Transactions on Information Theory 2018B. Okay, and the third related work is Avner and Manor in 2016. Okay, we can see that Avner and Manor, multi-user lax communications, a multi-armed bandit approach, in the 35th Annual IEEE International Conference on Computer Communications, InfoComm, in 2016. Okay. And the last related work is Avner and Manor in 2018. Okay, here. Avner and Manor, multi-user communication networks, a coordinated multi-armed bandit approach. Okay, we archive preprint, which is published in 2018. Okay, channel assignment algorithms have been developed under partial observation models using distributed learning. Another related approach models the spectrum access problem as a graph coloring problem, in which users and channels are represented by vertices and colors, respectively. Thus, coloring vertices such that two adjacent vertices do not share the same color is equivalent to allocating channels such that interference between neighbors is avoided. See the following four related works. Okay, the first one is Wang and Liu in 2005. Okay, let us see Wang and Liu list coloring-based channel allocation for open spectrum wireless networks in IEEE Vehicular Technology Conference in 2005. And the second related work is Wang et al. In 2009. Okay, Wang et al. Improved algorithm of spectrum allocation based on graph coloring model in cognitive radio in WRI International Conference on Communications and Mobile Computing in 2009. And the third related work is Checo and Leith in 2013. Okay, Checo and Leith learning-based constraint satisfaction with sensing restrictions, which is published in IEEE Journal of Selected Topics in Signal Processing in 2013. Okay, and the last one is Checo and Leith in 2014. Okay, Checo and Leith. And the paper title is Fast, Responsive Decentralized Graph Coloring. Archive preprint in 2014. And the references therein for related works. However, generally, spectrum access problems are more involved when the number of users is much larger than the number of channels. Thus, coloring the graph may be infeasible. Furthermore, users may select more than one channel and may prefer some channels over others, as well as optimize their rates with respect to the attempt probability. Okay, next section, section 1.3.3 is the deep reinforcement learning for DSA. So we are formally going to the door of the machine learning. Okay. The spectrum access algorithms that we discussed in the previous section mainly focused on model and objective-dependent problem settings, often requiring more complex implementations. For example, carrier sensing, wideband monitoring, and thus the solutions cannot effectively adapt in general for handling more complex real-world models. Therefore, in this section, we overview the very recent developments of a deep learning-based approach to overcome these issues. Specifically, we now focus on model-free distributed learning algorithms to solve equation 1.9. Okay, this equation. Okay, the maximum of expectation of capital Rn of sigma n and sigma minus n, and the variable is sigma n. Okay, do you remember what is capital Rn? Okay, The expectation of capital Rn of sigma n and sigma minus n denote the expected accumulated discounted reward when user n performs strategy sigma n and the rest of the user performs strategy profile sigma minus n. Okay, that can effectively adapt to changes in network topology, objective functions, time horizons, in which solving dynamic programming becomes very challenging or often impossible for large capital T, etc. Okay, what is capital T means? Okay, let us go back and to review this symbol. Okay, capital T is the time horizon, okay, on page 63. And I have explained what is time horizon. If you forget it, please review the handout. Okay, etc. Obtaining an optimal solution for the spectrum access problem considered here, however, is a combinatorial optimization problem with a partially observed network state that is mathematically intractable as the network size increases. Please see Zhao et al. In 2007. Okay, Zhao et al. Okay, there, and the paper title is Decentralized Cognitive Mech for Opportunistic Spectrum Access in Ad Hoc Networks, a POMDP framework, which is published in IEEE Journal on Selected Areas in Communications in 2007. Okay. Therefore, in this section, we overview methods that use a deep reinforcement learning DRL approach due to its capability to provide good approximate solutions while dealing with a very large state and action spaces. We first describe the basic idea of Q-learning and DRL. We then overview recent developments of DRL to solve the DSA problem. Okay, do you remember what is DSA? Okay, let us search for it. DSA. Okay, DSA means the dynamic spectrum access. Okay, let us go back to section 1.3.3. Okay. Okay, first let us look at the section 1.3.3.1, background on Q-learning and DRL. Okay, Q-learning is a reinforcement learning method that aims at finding good policies for dynamic programming problems. Sorry. It has been widely applied in various decision-making problems, primarily because of its ability to evaluate the expected utility from among available actions without requiring prior prior knowledge about the system model and its ability to adapt when stochastic transitions occur. Okay, please see Watkins and Da-Yang in 1992. Okay, this is Watkins and Da-Yang. Okay, the paper title is Q-Learning, and which is published in the journal Machine Learning in 1992. Okay. The algorithm was originally designed for a single agent who interacts with a fully observable Markovian environment, in which convergence to the optimal solution is guaranteed under some regularity conditions in this case. It has been widely applied to more involved settings as well. For example, multi-agent, non-Markovian environments, and demonstrated strong performance, although convergence to the optimal solution is open in general under these settings. Assume that we can encode the entire history of the process up to time t to a state S of t that is observed by the system. By applying Q-learning to our setting, the algorithm updates a Q value at each time t for each action state pair as follows. Okay, Q of t plus 1 of Sn of t and An of t, okay, where Sn of t is the state, okay, up to time t, and An of t is the action at time t. So this is called an action state pair. And Qt plus 1 is the Q value at time t plus 1. And it is equal to Qt of Sn of t, An of t, plus alpha times Rn of t plus 1 plus gamma, maximum of Qt of Sn t plus 1, An of t plus 1, over An of t plus 1, minus Qt of Sn of t, An of t, where Rn of t plus 1 plus gamma times the maximum of Qt of Sn t plus 1 and An of t plus 1 over O An t plus 1 is the learned value obtained by getting reward R of t plus 1 after taking action A of t in state S of t, moving to next state S of t plus 1, and then taking action A of t plus 1 that maximizes the future Q value seen at the next state. Okay, so please notice that this term, okay, equation 1.11 is equal to this term. Okay, this term. Okay, so we say that it is the learned value obtained by getting reward R of t plus 1. Okay, here is the R of t plus 1. After taking action A of t in state S of t. Okay, this is the action action A of t, and this is the state S of t. Moving to next state S of t plus 1. Okay, this is S of t plus 1. And then taking action A of t plus 1. Okay, this is A of t plus 1. And we need to take the maximum of this Q value over all possible action an of t plus 1. Okay, now it's 25 minutes. Let us take a break.